Hi folks, this is the Chem 151 lecture to make up for the snow day we had on February 26th, Tuesday, at least a late start. So this is to clean up the final discussion in the moles chapter, and we're going to talk about empirical and molecular formulas right now. We should have previously watched the percent composition video where we were determining the fractional percent of an element in a compound. But now I want to extend this a little bit more and do some other types of percent composition problems. And to do that, we need to introduce these concepts of molecular and empirical formula. So the first thing we already know, that's a molecular formula. It's a written formula that expresses the number of atoms of each type in a molecule. So for instance, if we had this compound N2O4, which we know from our nomenclature is dinitrogen tetroxide. Let's see, hang on, my animation's not working very well. So dinitrogen tetroxide. We know that this molecule has 2 nitrogens and 4 oxygens. Okay, that makes sense. Now there's another concept we want to introduce further called empirical formula. Now empirical formula is the smallest ratio of atoms in a molecule. So for N2O4, we know that there's two nitrogens and 4 oxygens. If we instead divide by 2, we get NO2. So this has a ratio of 1 nitrogen atom to 2 oxygen atoms. So that is the simplest way we could represent N2O4 in an empirical formula. Empirical versus a molecular formula. And this will become useful when we start doing percent composition problems, and we'll do that on the next slide. So empirical is the simplest ratio between the atoms in a compound, and then a molecular formula is the full compound itself, or the full molecule, like N2O4 versus NO2. Okay. Get my text off of this. All right. So, move on. Now, this is an exercise I would have done in class, but if we looking at this chart, if we know we have an empirical formula of 1 carbon and 1 hydrogen, we're going to have a molecular formula that is more complex. So more complex than just 1 carbon and 1 hydrogen. And so the molar mass listed in the center is for a molecular formula. Molecular mass. Okay, so if I take 1 carbon, which I know is 12.01 grams, and I take 1 hydrogen, which I know is 1.01 grams, then that equals 13.02 grams. And that 13.02 is less than 26.0, right? So what that means is that my molecular formula is going to have more atoms in it than just 1 carbon and 1 hydrogen. And we can find out what this multiplier ratio is by taking 26.0 grams per mole divided by 13.02 grams per mole. And that winds up giving us 1.999 for this ratio. And we're going to round that to 2. Put an arrow, round that to 2 because we know we can't have a 0.999 of an atom. So what that tells us is the formula is not the molecular formula is not CH, but instead we multiply each one by 2, and that gives us C2H2. And so C2H2 has a molar mass of 26.0 grams per mole. And comes in. And then the empirical formula is the simplest way to write that ratio. We divide each of these by 2, we get 1 carbon, 1 hydrogen, and that's our empirical formula. Okay, so for the next problem, if we have 1 carbon, 1 hydrogen, 1 oxygen, we wind up getting 1 carbon at 12.01, 1 hydrogen at 1.01, and 1 oxygen at 16.00. We have 29.02 grams per mole. We can find out what our multiplier ratio is again by taking our molecular molar mass divided by our empirical mass. And that will give us the multiplier ratio. So if we have 116.1 grams per mole divided by 29.02 grams per mole, find out that that's equal to 4.00. So therefore, we know that our ratio has to be 4 carbons, 4 hydrogens, and 4 oxygens. Okay, and then finally, if we look at C8H16, we can divide each of these groups by 8, the smallest of the number, and that will give us C1H2. And we, out of convention, don't write the 1, so that gives us CH2. All right, and then we can also calculate the molar mass of the molecular formula by taking 8 carbons and 16 hydrogens, and that will give us 112.2. So this concept demonstrates that we can take a molecular formula and we can simplify it to the smallest ratio numbers, which are whole numbers, between the individual components of the compound. Okay, so let's do another problem. And below, this is the math that I just wrote out here by hand. This is much more legibly typed. Okay, so this is a typical percent composition problem. So there's a couple of steps here, and if we follow those steps, we'll always be able to succeed. So the problem reads that through a chemical analysis that you would learn about in Chemistry 222, a compound of carbon and hydrogen is composed of 92.26% carbon. What's the empirical formula? Okay, so the first trick is we don't know really how much compound we're talking about, so we have to assume a certain amount. So if we assume 100 grams total, then we can determine the moles present. So let's go on the next slide. So if we have instead 92.26, not percent by weight, but then we transfer that and call that grams. So this is a key step where we just assume the percent is not a percent number, but rather a gram number. And we have to assume 100 grams to do that. So then if we have 92.26 grams of carbon in a 100 gram total compound, we can then convert that to moles. And that gives us, grams of carbon, cancel grams of carbon, leaving us with moles. So we have 7.68 moles of carbon. And then the remaining part of the compound is 100% minus 92.26%, or 7.74% hydrogen. Just like our same trick, we convert percentage to grams, so we get 7.74 grams of hydrogen. We can convert that to moles, just like we did with carbon, and that gives us 7.66 moles of hydrogen. Okay, so now we have moles of carbon, moles of hydrogen, and the next step is to write a preliminary formula. So this is the way I like to do it. We write carbon with 7.68 moles and hydrogen with 7.66 moles, but we need that to get into the smallest number possible. So we need to get that into an empirical formula. So if we divide by the smallest amount of moles present, which is the 7.66, that will give us one hydrogen here, and 1.002 or so carbons. When we round that to 1, because we can't have fractional atoms. So that winds up being C1H1, and by convention we don't write the 1s, we just write it as CH. And just like we did on the previous slide, if we determine that the molar mass of this compound is something greater than just 12.01 grams per mole plus 1.01 grams per mole for this compound, giving us 13.02. If we find out that the molar mass of the compound is something greater than that, then we have to find out what the multiplier is. And we determined on the last slide that the multiplier between 13 and 26 was 2, so that compound winds up being C2H2. So that's how we can do a standard percent composition, where the trick really is to assume 100 grams, then find the moles of each of the individual components. In this case, we went moles of carbon, then we had found moles of hydrogen, finding the difference between 100 and carbon percentage. Then we write a preliminary formula and divide by the smallest amount of moles. Good. Let's do another one. So if we had a compound that was analyzed and was determined to be 81.10% boron, and the remaining portion of the compound is hydrogen, we're tasked to find the empirical formula and the molecular formula if the molar mass is this. Okay, so let's assume 100 grams total. That's how we start. And then we'll find moles. So if we have 81.10 grams of boron present, remember we went from percent units to assume gram units. because we had 100% gram total compound. If we take 100.00 minus 81.10, we're left with 18.90 grams of hydrogen. That's where the grams of hydrogen came from. We can now find the moles by multiplying by the molar mass. Grams of boron cancel grams of boron, giving us 7.502 moles of, not carbon, but boron. Great. Okay, then we can do the same with hydrogen. Divide by the molar mass. Grams of hydrogen cancel grams of hydrogen. And we're left with 18.7 moles of hydrogen. All right, then next we'll want to write a preliminary formula of B 7.502 coming from here, H 18.7, then we divide by the smallest, and we're left with B1H 2.49. But that's a little bit confusing, right? Because where do we go from now? We know we can't have half of a hydrogen atom, and resist the temptation to either round up or round down. Instead, the trick that we do is we have to multiply by a number, the smallest number, to get a whole number ratio between atoms. So in this case, if we multiply each of these moles by 2, we'll get a B2H5 compound. So that is the smallest ratio, 2 atoms of boron to 5 atoms of hydrogen. Okay, so now that we know we have the simplest ratio, simplest whole number ratio, we can ask ourselves, does this have a molar mass equal to 53.3 grams per mole? Is that the case? Let's check. So if we add up the molar mass, we find that B2H5 has 26.67 grams per mole, but our compound is 53.3 grams per mole, so we're not done yet. So in order to figure out this multiplier, we divide our molecular molar mass by our empirical molar mass, and we find that ratio being 2. So therefore we have to take boron 2 times 2 and hydrogen 2 times 5. It's going to give us boron 4H10. Erase that. Okay. So we wind up with our molecular formula of B4H10 and our empirical formula of B2H5. And this molecule has a common name called tetraborane, which looks like this. Okay. Our conventional naming would say that this was diboron pentahydride. Diboron pentahydride. Okay, so that's how we use empirical and molecular formulas. Typically for percent composition problems, you will first find the empirical formula, and then, so for percent composition, you will first find the empirical formula, and then you will transition to a molecular formula, but only if you know more information, like the molecular molar mass.